have a new colloquium of the series postdoc on the spot. The postdoc is Leonardo Pipolo de Gioia, who is postdoc here in IFT and ICTP-SAIFR. And the title today is Implications of Asymptotic Symmetries on Scattering. And he promised me that he's going to give a comprehensible colloquium, okay? Let's check it. Thank you very much.
First, let me thank George for the invitation. And yeah, I'm going to be speaking about the implications of asymptotic symmetries on scattering. So here's one outline of what I'm going to be talking about. So I'm going to be talking first about the definition of asymptotic symmetries, and about asymptotically flat spacetimes, which is the situation I am interested in. Then I'm going to talk about how this translates into statements about the S matrix, and finally, how this motivated a conjecture called celestial holography conjecture. And then finally, I'll relate that to a flat space limit of AD-SCFT. So first, asymptotic symmetries. So there's an interconnection between two different subjects that have been studied separately for a long time. One of them is asymptotic symmetries, which are basically local symmetries with non-trivial action at infinity, as I'm going to explain in a moment. And the other is soft theorems, which are factorization statements of the S matrix 1 when one includes one extra particle and takes its energy to 0, one massless particle. And these two seemingly unrelated subjects are actually connected by a very precise relation. So first, to explain asymptotic symmetries, I'm going to use a language which is the covariant phase space language. And this is basically just Hamiltonian mechanics written for fields. And the basic point is that a phase space is, in this language, a symplectic manifold, by which I mean one even-dimensional smooth manifold equipped with one closed and non-degenerate two-form called the symplectic form, which is, well, this is the statement, right, of non-degenerate. And the basic idea of this language is then that a symmetry is a symplectomorphism, so it's a map from phase space into itself that preserves this symplectic structure. And infinitesimally, if it's generated by some vector field on phase space, the leaf derivative of the symplectic form should be 0. And there's a condition for that, which is that when you plug the symmetry generator on the symplectic form, you get a closed form, which is the charge that then generates the symmetry. So the idea of, not yet, I'll make it in a moment. And well, the idea of the covariant phase space is to use this language, which is just Hamiltonian mechanics, for fields, for field theory. So the idea is that the phase space is going to be taken as some subset of the space of solutions to the classical equations of motion, and variations of the fields are interpreted as curves in that space, and the first variation that we are used to are tangent vectors. So the idea is that a prescription assigning to it each field configuration a first variation is a vector field. So there's an algorithm that has been studied for a long time. I'm citing this paper of Leon Wald, but there's several others, that allows you to construct the symplectic form on this phase space. And the idea is that any variation of a Lagrangian form takes this general form here, where E are the equations of motion, and one gets one extra term here, which is called the presymplectic potential density, from which one constructs this anti-symmetrized variation. And then if one integrates over Cauchy slice, one gets the symplectic form. So that's a prescription, it's an algorithm. One can take any Lagrangian and go through this. And the idea then of the covariant phase space is to use this symplectic form to study the symmetries by the procedure I said. So one plugs here the symmetry action on the fields, and then tries to write this as the variation of a charge.
Sorry, I'm really
Yeah.
slow, so
Okay.
you're going a bit fast for me. So the variation Lagrangian depends only on the variation of the field, and how about the variation of the derivative of the field?
It's encoded here.
Is encoded where?
It's because, I mean, the idea is that what happens is that we use the product rule of the derivative several times to extract a term which is proportional to the variation of the fields, and all remaining terms containing derivatives are contained here.
So you're integrating by parts.
Yeah, exactly.
And that's a total derivative.
Exactly. That term, when we integrate and assume everything goes to 0 at infinity, will not contribute, but it encodes the data that defines the symplectic form. That's the idea.
Are you going to give an example?
Huh?
Are you going to give an example
Of this?
Yeah.
I'm going to give an example of the charges.
of omega? I'd like to see a non-trivial omega. I mean, I'm used to seeing the trivial omega, but what's a non-trivial example of omega?
Well, yeah, I mean,
So I'm used to just omega is x with p, and p is, the derivative of Lagrangian with respect to x dot. Is it more complicated than that? Do I need to think of something more complicated than that?
yeah, okay, I can write one. I don't have it in the slide, but I can. Yes. Sorry?
Classical mechanics.
Well,
in the case of particles.
well, yeah, I'm not sure. I mean, this
It's
is
called a Louis form. This.
Yeah, I mean, in this case here, one can do that for classical mechanics as well. It's just then finally many degrees of freedom. Yeah, for example, for electrodynamics, it's just, for example, if one does that for electrodynamics, it's F wedge delta A. It depends on the fields and the variation. So it would be something like F wedge delta A.
Okay.
The integrand, integrated over a Cauchy slice.
Okay.
That's an example.
Okay.
Well, and then, I mean, this theta here is a d-1 form in space-time, and a 1 form in field space. This omega is a d-1 form in space-time and a 2 form in phase space because of this exterior derivative, and omega is a 2 form in phase space. So the idea then is that's the distinction now between local and global symmetries, is that for local symmetries, there is an identity called Noether-Second theorem, which basically tells us that if we plug here a local symmetry, we get a total derivative of another form. We get an exact form. So for a local symmetry, what happens is that this thing here is actually a boundary term in the boundary of the Cauchy slice. And since sigma is a Cauchy slice, this is essentially at infinity, as I will exemplify in flat space in a bit. So there are basically 3 situations that can happen. One of them is that this integral over the boundary of the Cauchy slice will basically vanish for any variation of the field. If that happens, that symmetry generator gives a degenerate vector of the symplectic form, so it's degenerate, so it's not yet a symplectic form. This can be remedied with gauge fixing. The second is that we get the form that we want, and we identify a Hamiltonian charge for that symmetry. And the third is that the integral is non-zero, but it's not of this form. It's not the total derivative, but there's something else. And then we call this a non-integrable charge. Well, the first case is the case which is most common, which is that we have the degenerate vectors of the symplectic form, and they must be eliminated by gauge fixing. The other case defines what's an asymptotic symmetry. An asymptotic symmetry is exactly one local symmetry with non-trivial action at infinity, so that this happens and one has a non-vanishing charge here. And these asymptotic symmetries are defined, of course, modulo the trivial gauge symmetries, which are the ones that are trivial at infinity. So this defines what we call the asymptotic symmetry group. Yeah.
You were being very careful and mathematical, and then you suddenly throw out the words infinity, which you don't tell us what it is. So it's some non-compact space, and
I will exemplify in flat space in a bit. This is general, I mean, and could be any space-time, and then I'm saying it's infinity because since this slice is Cauchy, the boundary is at infinity, but I will exemplify that in flat space in a few slides.
I mean, you're going to have to tell us what an integral is if you're doing it over in some infinite region, right? You're going to have to tell us.
No,
how to
but that's
compact
not an infinite region. That's going to be over a sphere.
Okay.
I'll exemplify it in a bit. So this definition of the asymptotic symmetry group. And as I said, I mean, basically the trivial gauge transformations are the ones we gauge fix. So these ones are the ones we want to gauge fix, and that's the gauge fixing in the classical story. So after gauge fixing, then the asymptotic symmetries just become the residual gauge transformations.
Just to go to something I understand.
Okay.
So QED, right, has
Yes.
a local symmetry. Is that asymptotic symmetry, or
You can. If you allow for gauge transformations that are non-vanishing at spatial infinity, if you allow for that, those are the
Yes.
asymptotic symmetries of QED. The reason why most of the time people don't talk about those is that it's because people are assuming that the fields all vanish at infinity.
Right.
If you assume a non-trivial fall-off with 1 over r, the radial direction, you can have these asymptotic symmetries.
is there a physical example where that happens? Any physical theory?
Yes. Well, for example, these asymptotic symmetries in QED, they give, for example, the soft photon theorem, as I'm going to explain. I will explain in gravity, but in QED is the same story. So the asymptotic symmetry is related to a one non-result for the S matrix.
So you have a QED theory or mod or setup where the fields don't vanish at infinity,
Yes.
or vanish slower than 1 over r squared, for
Yeah.
instance, or 1 over
Yes.
r.
Yes. And for example, people, I will not go into this here, but people have argued that if you want to keep track of these symmetries, one is able to define one S matrix which is infrared finite, which does not vanish as usually happens.
Right. But if you have a system of charges and electric fields, does that happen?
Yes. For example, the most trivial
Yes.
field configuration that happens is the Leonard-Wickard configuration.
Linear?
Leonard-Wickard, for moving charges, just a collection of charges moving on geodesics, that thing generates a field configuration like that.
Okay.
Well, so what we want to do is to apply this for asymptotically flat spacetimes. So these can be defined in the gauge fixing approach as done by Bondi, Vanderburg, Metzner, and Sachs in the 60s. So one chooses a gauge. The most common is Bondi gauge, which is defined by these conditions here. And then one imposes some fall-off conditions on the metric, which are basically this. So the metric at large R is basically the Minkowski metric plus corrections. And these corrections encode the gravitational data. So this is the Penrose diagram of asymptotically flat of Minkowski space. The idea of an asymptotically flat space is that at infinity it looks the same as Minkowski space, but in the interior it might be very different. So this scry plus is null infinity, which is where massless particles go to, and this scry minus is where massless particles come from. And these are the boundaries of scry plus at the past and the future. Same here, and this I0 is spatial infinity, which is large distances at fixed time. And I minus and I plus are the time-like infinities, which are where massive particles come from and go to. But in this talk, I'm just going to focus on massless particles, so I minus and I plus will not play a role here. So the gravitational data I was speaking, and by the way, just going back to Nathan's question, in that case, the Cauchy slice would be actually, in the absence of massive particles, it would be essentially scry plus, and the boundary is this scry plus minus, which is a sphere. So the integral, this thing is at infinity, and the integral is in a sphere that approximates I0 from scry plus. So that's why I said that it's something at infinity. So the gravitational data that we read from the metric is basically this Bondi mass aspect. The gravitational shear disappears on the GUU component, is on the sphere components. This AB are instances on the sphere. This NAB is basically what we call the Bondi news and encodes information about gravitational waves. And we also, at further subleading orders, I didn't write, but we also find this Bondi angular momentum aspect. So these are the data describing the gravity field there. And I mean, these is like a density of energy, and this is like a density of angular momentum. But I'll exemplify that with the charges that come from this covariant phase space in a bit. So now one can look for the asymptotic symmetries, and they are the residual gauge transformations. So they are basically diffeomorphisms that preserve boundary gauge and also preserve the fall-off conditions. And these have been studied by Bondi, Vanderburg, Meissner, and Sachs in the 60s, and they found what's called the BMS group, which is basically an enlargement of the translations in flat space to something called supertranslations, keeping Lorentz transformations. So this is a depiction of the action of supertranslations, and they basically translate along the null generators of Scry. Scry is basically R cross S2, and one translates independently I mean, for each angle, one has a different displacement along the null generators. That's what a supertranslation do. On the other hand, Lorentz transformations at infinity, they just act as the global conformal transformations of the cross-sections of Scry. So the cross-sections of Scry are spheres that we call the celestial sphere, and Lorentz transformations are just the Mobius transformations of the sphere. They're just conformal transformations of the sphere. But these Barnich and Tresine, a few years ago, they suggested that one should also enlarge these global conformal transformations of the sphere to local conformal transformations of the sphere, which basically is the width algebra. Now, they didn't have a proper justification for that at the time, but as I'm going to explain in a bit, there is a possible justification that comes from the study of soft theorems. And then when we enlarge Lorentz to super rotations, which is this local enlargement, then we get something called the extended BMS algebra. And now, well, super translations, it's an infinite dimensional part because you have one super translation for each function on the sphere. And if you just get the global conformal transformations, it's finite dimensional. But if you enlarge, you have infinitely many, which is the standard Virasoro generators. Okay, well.
It is like me.
Yeah, super translations, they are basically, they act at infinity as like a function of the angle.
Write it down, x goes to x plus something, or?
No, we do, okay, the finite super translations are more subtle. Infinitesimally is just this, right?
Infinitesimal is fine.
Infinitesimally is, they're generated by vector fields of this form near infinity, where these are one over R corrections, where this is a function on the sphere. This is some arbitrary function of the angles. So that's why I'm saying that they just displace along the U direction in an angle-dependent way. So at each angle you are, you have a different displacement. And for example, the translations, if you restrict F to be in the space
Sorry,
span.
what is Z and Z bar?
These are the coordinates on the sphere. They're the standard stereographic coordinates on the sphere. And if you restrict F to be in the span of these spherical harmonics here, you recover the standard translations, the standard rigid translations. So for example, F equals to 1 is the time translation, is d by du.
May I rephrase Nathan's question, because this is my question too. So I think I can write down a translation field, time-like translation field, just looking at your arrows there.
Yes.
So the question is, what makes this translation to deserve the qualification of super translation? What's the property, the special, very special property that this translation field has to deserve this qualification?
What sets it apart from the standard translations? Well,
yeah,
I mean,
what's special about this translation of, usual translation?
Well, a few comments is that first, we just get super translations if we have gravity, and they are not symmetries in they are asymptotic symmetries. So they are they obey the Killian equation just asymptotically, just like when you take R to infinity. They're not they're not isometries of the spacetime. They just preserve the metric at infinity. So they preserve this part here of the metric.
Sorry, what is R? You keep
R
saying
is the radial. R is the standard
But
radial.
Minkowski space doesn't have a center. So what does R mean?
Well, it's defined by the boundary gauge, right? you choose a set of coordinates that satisfies this. The R coordinate is the analog of the radial coordinate in spherical coordinates. And it's what we are using here to reach infinity.
Suppose I move from polar coordinates to some other coordinate system. Is there a natural definition of R?
Well, okay, one can also define this in other gauges, in other
And
coordinate
does a
systems.
super translation stay a super translation if I redefine what I'm calling R?
Right. This part here of the super translation field, which is basically the restriction to null infinity, this part is independent of the choice of gauge. What comes next, the corrections are dependent.
I see. Okay, thanks.
But the leading term, the behavior exactly at scry, which is this translation along the generators, they are, this thing is here, is gauge independent.
So all the physics comes from the first term. The dot, dot, dot has no physical meaning. Is that what you're telling me?
I mean, yeah, what they do in the interior of the space-time is, in a sense, I mean, there are many discussions of that. There's a,
Okay.
but
Okay.
but it's not clear. I mean,
Okay, thanks.
Right. So going back to the charges, I mean, as I said, one can go to this covariant phase space procedure and define the charges associated to the super translations and the super rotations going to that algorithm. And one finds these two charges here, essentially. So this is the super translation charge, and this is the super rotation charge. And for example, when one sets here, these are integrals, as I said, on scry plus minus, which is basically the pass boundary of scry plus. There's an analog story at scry minus, so one has outgoing charges and incoming charges, which in the classical theory are conserved in the sense that the incoming ones match the outgoing ones. And, well, if you set F to be the rigid translations, you recover the momentum components. And if you restrict this to be the Lorentz transformations, not the local vectors, you get the angular momentum components. So that's basically the charges. And now one can try to understand what this implies for scattering. So in scattering, the observable we care about are scattering amplitudes, which is, yeah.
Okay, but these charges are not strictly conserved, no? Because we know that only the real mass and the real angular momentum are conserved. I mean, when your F and your capital Y are non-trivial, basically it's like taking moments of the mass and taking moments of the angular momentum, and these other charges are not conserved. No, suppose, I mean, this F could be whatever, no?
Yeah.
But then, if this F...
there is a class of spacetimes in which they are conserved. The class of, I didn't go through this because I was going to discuss in the quantum version instead of the classical, but the classical version of the story is that they are conserved if the boundary mass aspect and the angular momentum aspect at scry plus and scry minus are antipodally identified near spatial infinity. So if you impose that this thing here is equal to m at the antipodal point at scry minus plus, then this thing is conserved.
You mean m independent of x?
Dependent of x.
Still dependent on x.
Then it is conserved, provided, of course, you also choose the subgroup of the cross product of BMS plus and minus that also satisfies the antipodal matching.
No, but this, I mean, your F...
There's a class of spacetimes where this happens.
I mean, very simply, no? Your F depends on angles. M depends on angle. Basically, the integral is picking the sum of the two angular distributions such that one cancels each other. Basically, is picking the spherical harmonic L equal to 0 of the product of the two.
Yes.
Okay.
That's true, yeah.
Okay. And still that gives rise to an infinite amount of charges?
Yes.
Okay.
But to have conservation on the classical theory, you need to antipodally identify this M close to I0.
Okay.
There's a class of spacetime where this happens, but it's not clear that it happens in general. That's true.
But still it can depend on the angles. Also
the result of the integral? No, right?
No, inside the integral.
Yes, yes.
Just to see if I understand. So you have a BMS group associated with scry minus, another one associated with scry plus, and in order to connect these two things, you are imposing that, what you said, that K plus associated with Scry minus is equal to K plus
Yeah.
associated with Scry plus, is
Yes.
it?
Yes.
How strong is it?
It seems to be quite strong, actually, and I mean, there's a class of spacetimes that have been shown to obey that, which was proved by Christodoulou and Kleinemann when they were studying the nonlinear stability of Minkowski space. People have been assuming this boundary condition and studying the consequences, but there is also another thing, which when we go to the quantum theory, soft theorems imply this thing, imply the conservation of the charges and then this matching. So one suspects that, I mean, since one can just prove the soft theorems independently with Feynman diagrams, that there's the chance that this could be more general. But I agree that there is no proof that it is, how strong that is, yeah.
Going back to Rogério's question, suppose we do just QED in flat space-time.
Yes.
What's the analog of these charges?
Well, then what one gets is basically one integral of at Scry plus minus of basically the gauge parameter times F UZ, for example, the component of the field strength UZ. And then, I mean, these charges, for example, again, the example I gave, if one studies the Leonard-Wickert solution, one can compute these charges explicitly and see that the Q plus equals the Q minus.
So they're conserved, that's what you're
Yes.
telling me. Okay.
Well, so on the quantum version of this, we want the charge to commute with the S matrix. That's basically the quantum statement of the symmetry. And we can do this for these charges of the BMS or extended BMS algebra, basically by writing the Q's in terms of creation annihilation operator of gravitons. So then we're working in perturbative gravity and expanding about flat space. So when one does that, and I'm not going to give the technical details, but just explain the idea is that these charges decompose into a term which is linear in the gravitational field and quadratic. The linear part is what we call the soft part, and the quadratic part is what we call the hard part. The reason is that the linear part is actually related to modes of the gravitational field with zero energy. So it encodes the limit of graviton creation annihilation operators when we take the energy to zero. And the other, no, the other, it contains radiative degrees of freedom. So to establish asymptotic symmetries at the level of the S matrix, one needs to study this low energy expansion of the graviton here. And well, fortunately, this has been done. That's what I mentioned in the beginning, which are the soft theorems. Soft theorems say that if you add, for example, a graviton of some arbitrary helicity on the outgoing state and expand at small energy, you get a factorization where you have a soft factor times the S matrix without a graviton. The leading soft factor was found by Weinberg, and it's basically this expression. It's a pole in the graviton energy, while the subleading soft factor was found by Cachaza and Strominger, and it's a regular, but it's also an operator acting on this amplitude. These are the angular momentum operators acting on the scattering amplitude. So these are statements that can be made just using Feynman diagrams and just studying amplitudes in quantum field theory. And they allow you to compute, well, they allow you to compute exactly this insertion here, this commutator here. And it turns out that when one goes through that and use the soft theorem, computes the charges, and computes that commutator, the soft theorems imply the asymptotic symmetries. It's actually stronger than that. The asymptotic symmetries are equivalent to the soft theorems. They also imply the soft theorems. With a caveat that for the superrotations, one needs to further enlarge instead of just allowing that vector field Y to be a conformal Killing vector on the sphere, to have the converse of the statement, one enlarges to be any vector field on the sphere. But yeah.
Sorry, so the soft theorems, are they perturbative?
Yes.
And the asymptotic symmetries are perturbative as well?
Well, in this language, we are using the soft theorems to prove the asymptotic symmetries. So it depends on the soft theorem, because, for example, this soft theorem here, the leading soft theorem has no corrections. It's an exact statement. So we can say that, well, This gives the this one gives the super translation symmetry. So since it is an exact statement, we can say that the super translation symmetry is also an exact statement. But this one was found at tree level. So the super rotation symmetry was established at tree level. Then people studied loop corrections. I'm going to comment on that. Yeah, I'm commenting here. Then people studied loop corrections to that, to the subleading soft theorem, to try to understand corrections to the super rotation symmetry. And they found that usually one has one IR divergent correction, but the symmetry survives after you renormalize the generators in an appropriate way. So that's the status of these two. These two, I mean, yeah, we believe that these super translations and these super rotations, we expect them to be exact symmetries.
So what do you mean evidence has been provided? You mean one loop? Is that what evidence means? Or what does evidence mean?
The correction at one loop is exact. The infrared divergent part, I mean, the correction to the subleading soft, this thing here can get corrections. It has one infrared divergent correction, which is one loop exact. What appears at one loop is just that. It could also have finite corrections. The finite corrections were shown to not arise in examples, but there is no general proof that they are not there. But at least this infrared divergent correction was shown to be like, this one is one loop exact, and it was shown to be possible to deal with it with the renormalization of the generators.
So it's not known if it's corrected or not. That's essentially what you're telling us.
No, about the finite ones, no. Yeah? Yes.
There is also a sub-subleading term with two-loop correct.
Yeah, exactly. Yeah,
two-loop finite. Yeah.
Yeah. I'll talk a bit about the sub-subleading, but then it's more complicated.
Probably you want to draw the triangle as well. Too.
Yeah. Yeah, maybe in a bit. But let's see how I'm with time. Yeah, I need to speed up a bit. But well, so I'm just going to make some comments about these symmetries. If you take this for the super translation, if you take this special super translation here, you find that the statement of the asymptotic symmetry of that super translation symmetry takes this form, and if you take the super rotation, this one here, it takes this form here. This form here is reminiscent of a current insertion in a conformal field theory, and this to a stress tensor insertion in a conformal field theory. They resemble that. Now, the stress tensor one, I mean, what appears to be the weights, the conformal weights, are basically operators. It are not numbers as would happen in a conformal field theory. And the operators are basically these, and then one can try to understand scattering in a basis that diagonalizes these operators. Because then it will behave, the S matrix will behave even more closely to a conformal correlator.
This is very special about 4 dimensions, right?
No, work on generalized.
Oh, okay.
Yeah, it also works in higher dimensions. But then in higher dimensions, you don't have local conformal symmetry, but still you have these operator valued dimensions, and you can diagonalize by the same transform. Huh?
Scattering?
Massless particles.
Which particles?
Well, to have this identity, you need the graviton.
But gravity 2D is not dynamical, is it?
No, but it's not gravity in 2D, it's gravity in 4D.
Ah, gravity is in 4D.
This identity here is an identity on the celestial sphere at infinity, so it's in 2 dimensions lower.
Okay. Ah, okay.
So basically, the idea is that one can diagonalize those operators, so those dimensions, by this transform, which is the Malin transform. At the level of one particle states, it does that. At the level of wave functions, one, instead of scattering plane waves, one scatters these wave functions called conformal primary wave functions. This is just a choice of states to scatter. That's just it. We're just recasting the S matrix in a different basis. And then the amplitude and scattering amplitude in this new basis is what we call a celestial amplitude. That's the definition of a celestial amplitude or celestial correlator. And we define a celestial CFT to be some 2-dimensional theory whose properties we don't fully understand that can generate these amplitudes. The endpoint functions of these theories is a conjecture, should generate these amplitudes. But whether you believe that conjecture or not, you can still recast the S matrix in this basis and study the consequences of that.
Level or what?
You can define them at any loop level. And well, one often uses this notation just because these amplitudes resemble correlators, but it's just a notation at this point. So here are some results. I'm going to go through them in the next slide, in the next few slides, instead of going through this list now. And basically, first, I'm just going to comment on Poincare symmetry, which is the simplest thing that we can do. So Lorentz symmetry translates into the celestial sphere as global conformal symmetry, as I already mentioned. And then the celestial amplitudes transform under Lorentz symmetry as just a conformal correlator would under global conformal transformations, which is this formula here. Translation symmetry, on the other hand, does something a bit different, because the translation generators, the momenta, they act on these operators by weight shifting. They shift the weight. And this implies some non-standard features of these celestial amplitudes that are not present in standard conformal correlators. For example, this kind of identity here. It also implies that 2, 3, and 4-point functions have delta function singularities, as I'm going to exemplify now with the 4-point function. So the 4-point function, it takes almost the same form that in a standard conformal field theory. It has a conformally covariant prefactor that transforms as one would need for a 4-point function. But now the function of the cross ratios, which are the conformal invariants we built from 4 points, it contains a delta function enforcing that the cross ratio z and the cross ratio z bar are equal. So it enforces reality of the cross ratio. And the physics behind that is that you have 4 particles, they scatter in a plane, and this plane intersects the sphere at infinity in a circle. So this is basically saying that the 4 points must be on that circle, otherwise the amplitude is 0. So that's just what's saying. And it also, I mean, that weight shift in symmetry implies that the remaining function here of z and z bar just depends on the sum of the dimensions and not on the individual dimensions. So these are just some features of amplitudes in this basis. That's the form, the general form of a 4-point amplitude in this basis. The soft theorems that I have already mentioned, they translate into this basis as well.
Just
yes.
a quick question
Okay.
about the amplitude. So
Yeah.
you're scattering gravitons. So where are the helicities of the gravitons in this amplitude? Is that maximum helicity or suppression or?
Well, it depends on the helicities. Li's are the helicities.
Li are the helicities?
Yeah, exactly. So the dependence on the helicities is contained in this function.
What is beta?
And beta is the sum of the dimensions.
Okay.
Can you repeat what you said, that they all have to scatter in the same plane? Why?
By momentum
Why do they
conservation.
scatter in the same plane?
I have 4 particles. They scatter in a plane.
Is that true?
Yes, by momentum conservation.
I see. Okay, I didn't know that. Okay, thank you.
And then this plane defines this circle that is defined by
that
this.
part I understood. Okay.
Yeah. Well, the soft theorems, I mean, I'm going to go quickly through this, but soft theorems, they are statements about limits when the energy goes to 0. But so it would be, well, since we're integrating over all the energies to define these amplitudes, it's not clear how to translate soft theorems into this new basis. But it turns out that they do translate. You can actually take these deltas, these deltas are actually boost weights. They are eigenvalues of some boost generator. And you can take limits of this delta going to these values 1 minus s, where s goes 0, 1, 0, minus 1, etc. And when one does that, one encodes the soft theorems. Basically, one also has a soft factorization in this basis, but is now called conformally soft factorization. But it captures exactly the same physics. And this S is the subleading order. So F1 is the leading one, 0 is the, S equals to 0 is the leading one, minus 1 the 1 the subleading one, 2 the subleading, and etc. Another feature of this basis is that we can look to the collinear singularities of amplitudes. So if we take two external particles coupling through a three-point vertex to be collinear, so we take this limit, this kind of propagator develops a singularity of this kind. And so amplitudes develop this collinear singularity. And amplitudes are known to factorize when you have this. So the amplitude factorizes in terms of these splitting functions here, and you replace the two particles by a single one. That's an amplitude property that's been known for a long time. And one can take the Melling transform of that and recast that in the conformal primary basis, and what one finds is something that resembles, and I'm using the word resembles here for a good reason, and I can explain in a bit, but it resembles an OP, an operator product expansion in a two-dimensional conformal field theory. I'm saying resemble because at this moment there is no complete proof that this is actually an OPE that's associative and etc. But it resembles and it seems to endow this this celestial CFT with an OP. And this kind of structure has been shown to be also possible to fix using symmetry. So the symmetries fix the splitting functions in a sense.
So I'm still confused about the basis. So you have an equator, right, which you use to define z equals z bar, right?
Yes.
But if I have more than 4 particles, it certainly doesn't fix to
No,
a
then
plane.
no. Then you don't have the delta function.
But somehow, when I take the OP of 2 of these g's, it knows where the equator is. How does it know where the equator is?
These G's?
Yeah,
No.
so you say, so you have something which relates z bar with z, right? So it knows where the equator is.
But that just at 4 points, right? I mean,
No, but this is an OPE. This is supposed to be true for any point.
you're asking about how to use the OP inside the 4-point function to reduce to the 3-point function?
Well, a 5 point. I mean, an OPE is an OPE. It doesn't depend on how many.
Yeah, exactly.
points I have.
That's okay. That's exactly why I'm saying it resembles. Okay, I mean, there is no
I'm
complete
sorry,
proof that this is an
correct?
OP.
I'm not saying it's a proof. Is this what does that similarity mean? Is that an equal sign or?
This thing means
Yeah.
that it's equal plus subleading terms in Z.
And those subleading terms don't have this z bar symmetry property, do
The,
they?
the point about the subleading terms is that people understand, for example, if you keep Z bar fixed and you construct the whole series in Z, if you do that, that's what people have done and they understand that. If you try to put both Z and Z bar terms, then there are things that there are open problems there.
I see. Okay, thanks.
And well, and just a final thing about this, which is that the soft theorems, as I said, I mean, there's this leading and subleading soft theorems that imply in supertranslation and superrotation symmetries. But you also have sub-subleading soft theorem, and it goes through arbitrary subleading orders. And these also give rise to symmetries. And using this construction of the celestial OPE, people have been able to organize the generators of these symmetries into something called the Debye infinity algebra. So basically, there is a set of currents in this two-dimensional sphere that obeys an algebra, the Debye infinity algebra, and that encode the soft theorems and the soft symmetries to arbitrary subleading order. And one comment that I have is that this Debye infinity symmetry was also shown to be realized in classical GR. So expanding Einstein's equation close to null infinity, one can define these charges here. These are generalizations of the Bondi mass aspect and angular momentum aspect. And one finds these charges being extracted from the metric components, as happens for the Bondi mass and Bondi angular momentum. And one checks this algebra here at the level of the classical Poisson bracket. So that's a result that thing is independent of this celestial P. So it's an independent way of getting this Debye infinity algebra. Another comment is that in self-dual gravity, this is an exact symmetry. But away from self-dual gravity, we don't know. We need to understand corrections to this symmetry. Because possibly there are loop corrections, effective operator corrections, etc. So the idea, this raises a conjecture, which is called the celestial holography conjecture, that maybe there is a two-dimensional theory that reproduces these celestial amplitudes. And this two-dimensional theory resembles a conformal field theory in 2 dimensions in some sense. But there is no proof at the current moment that this disputative celestial CFT, if it's really a CFT, and or if it's something else, and then what properties it has. There is a construction for self-dual gravity. One knows how to construct this celestial CFT for self-dual gravity and self-dual Yang-Mills. But that's a very special case, and more generally, it's really an open question to construct these things.
You mean 2,2 signature? Is that what
Yes,
you mean?
2,2.
So it's not just a special
Yes.
case, it's a different signature.
Exactly, yeah, I know, I agree, that's true. I mean, that's why, I mean, then I get to, I mean, and I hope I have some time to talk about that, which is that that's the motivation for my work so far. That's exactly trying to produce a method to try to make top-down constructions away from the self-dual sector and in the right signature 1,3. And the idea of this proposal is to rely on a flat space limit of ADS-CFT. Actually, this is a motivation, but after the motivation part, one can just start from a three-dimensional conformal field theory and perform a kind of dimensional reduction and extract these amplitudes from conformal correlators. That's the basic idea. So in ADS-CFT, correlation functions in the dual CFT are computed by Witten diagrams. And there's an example for 4 points. And basically, the external lines are bulk-to-boundary propagators that the dimensions of these bulk-to-boundary propagators are the dimensions of the operators. Their insertion points are basically the points at which the operators are inserted in the CFT at the boundary. Internal lines are bulk-to-bulk propagators, which are just time-ordered Green's functions of the wave operator in ADS. And the vertices are just integrals over ADS with factors of the coupling, as in flat space. And a Witten diagram then computes contributions to a correlator like this. And the idea is that ADS, there's a limit in which ADS turns into flat space. Basically, if one rescale the global time and global radial coordinate in ADS by the ADS radius, the metric turns at large ADS radius into the flat space metric. And geometrically, it is zooming into a region near a point in ADS where the geometry turns flat. And there is an associated configuration at the boundary, which is when we place operators at 2 time slices at the cylinder, which are separated by pi in global time. And we place them around these 2 time slices, basically, in an infinitesimal strip. And the idea basically is this picture here. So we have this small region near the center of ADS that turns flat, and the operators are inserted into these strips, which are basically null separated from this region. And the idea is that if one puts operators in this configuration and studies Witten diagrams, one finds, and that's a motivation, that's not a rigorous argument, one finds that the Witten diagram turns into a Feynman diagram computing a celestial amplitude in flat space. Basically, the bulk-to-boundary propagators turn into conformal primary wave functions. The bulk-to-bulk propagators turn into Feynman propagators, and the vertices just turn into integrals over flat space. Of course, this is not a rigorous argument because it relies on exchanging a limit and an integral, but it motivates a conjecture that celestial amplitudes arise from 3-dimensional correlators in a conformal field theory through this prescription. We place the operators in that configuration. We need to antipodally identify the 2 time slices to get something which has the right symmetry. I can explain that if someone wants. And basically, one takes these integrals over these small regions here. And when one does that, I mean, for each dimension on the CFT, one generates a continuum of dimensions for this celestial CFT, which is expected. That's how we get a continuum of dimensions, because in flat space, that delta is just a boost weight, and it can take on any value, while in the CFT, deltas must be in the spectrum. So this proposal passed some non-trivial checks. The first check that I want to mention, well, the most recent check was an explicit example for 2- and 3-point functions that I'm going to mention in the end. But another non-trivial check is that we can recover the extended BMS symmetry from just conformal symmetry of the cylinder. So If one studies the conformal Killing equation on the cylinder, so one tries to find the generators of diffeomorphism that generates conformal transformations on the cylinder. If one studies that on that infinitesimal strip about a time slice, one finds an infinite set of solutions. One finds one vector field for each function on the sphere and each conformal Killing vector on the sphere. Now, this only happens when you take R to infinity, so when you collapse that infinitesimal strip to the time slices. Otherwise, the conformal Killing equations are broken. They're broken by like 1 over R terms. Unless F is a constant and Y is a global conformal Killing vector on the sphere. When that happens, we recover the standard conformal algebra of the cylinder. More generally, one recovers after doing something that generalizes the Inonu-Wigner contraction. One gets the extended BMS. So one gets super rotations and super translations obeying the correct algebra from the conformal Killing equation on the cylinder. Moreover, I mean, a conformal Killing vector acts on an operator like this in the CFT tree. And if one chooses these enhanced vectors that we found, and one computes this thing, one finds that in the large R limit, the primary operator in the CFT transforms as a two-dimensional primary with an operator value dimension, which is this. So this is what suggests that integral transform that appeared here. This integral transform diagonalizes the dimensions on the sphere, on the time slices. So basically, the operators in the CFT diagonalize dilatations in the cylinder, but they don't diagonalize dilatations on the time slices, and we can diagonalize those. So we define for each operator in the CFT a continuum of operators on the time slices. That's the basic idea. And they transform as we would like under the BMS algebra that we find from this enhanced conformal symmetry. And here's just a parallel between the standard Kaluza-Klein reduction and this celestial reduction. Because in Kaluza-Klein, what we have is we have this higher dimensional space, and then we have a mass Casimir on the higher dimensional space. Fields diagonalize this mass Casimir in the higher dimensional space, but not in lower dimensions. And then we do an integral transform diagonalizing these masses and producing a tower of fields. Here we have a field that diagonalizes dilatations in the cylinder, on the cylinder, not on the slices. But then we can diagonalize the dilatations on the slices by some integral transform, and that's how we get the continuum of celestial operators. Moreover, I mean, we can also extract from the stress tensor of the CFT the leading and subleading soft gravitons. These two operators, where this T tilde means basically the shadow of the stress tensor, these operators, they basically generate the leading and subleading soft graviton theorems. So this is consistent because we found at the level of the geometry that an enhanced conformal symmetry gives rise to the extended BMS algebra, but then we also find that the generator of conformal transformations give rise to operators that reproduce the leading and subleading soft graviton theorems, which imply in the extended BMS symmetry of the amplitudes. And finally, this proposal has passed another non-trivial check, which is an explicit check at the level of 2- and 3-point functions. Although it seems a very simple thing, it turns out that the proof that it really works like that is very non-trivial. And it involves the causal structure of the cylinder in a very fundamental way. It doesn't work, for example, in the Euclidean CFT, you need to be in Lorentzian. And basically, the 2-point function in the CFT is fixed. And if you go through that procedure, one finds exactly the correct celestial CFT 2-point function. The celestial CFT 2-point function is this. It follows exactly from the CFT 2-point function when you expand about those time slices and take those integral transforms. And the CFT 3-point function also works. Basically, what happens is that it's also fixed up to the OP coefficient. And if one also puts the operators in that configuration and expands at large radius and take the integral transforms, one finds that provided this OP coefficient is that of a phi-cubed vertex in ADS, computed through Witten diagrams, one generates exactly the correct celestial CFT 3-point function, with the correct singularities and the correct 3-point coefficient in flat space. But you need the right vertex, right? I mean, if you don't put here the OP coefficient coming from a phi cubed vertex, it doesn't work. So you match the vertices in flat space as predicted by the Witten diagram analysis. The phi cubed vertex in ADS gets matched to the phi cubed vertex in flat space. The remaining structure, I agree.
So what would happen if the vertex was not a phi cube vertex?
Then it would match another vertex, the corresponding vertex in flat space. The prediction is that the prediction is that the Witten diagram in ADS maps to the corresponding Feynman diagram in flat space. So the vertex you put in ADS will get mapped to some vertex in flat space. Then we checked explicitly, for example, the phi cubed vertex. This thing has been computed a long time ago and is known. So for this, we reproduce exactly the phi cubed vertex in flat space.
So this was not known. There are so many papers about flat space limit of ADS, and no one had done this trivial computation.
No. And well, one thing is that most results in that direction are for massive particles. Here is always massless. So that's an important point. I mean, we always keep these dimensions in the CFT to be, they don't scale with the ADS radius. So we always get massless particles in flat space. And another thing is that we're always working in this map to celestial amplitudes instead of, for example, I know that there are some other results using, for example, Mellin correlators at the level of 4-point functions, where one gets momentum space amplitudes, like amplitudes that depend on the momentum instead of these celestial variables. This goes directly from ADS, from CFT correlators to celestial amplitudes. And another comment, which is actually, this integral here means just a technical comment. This integral here actually can be traded simply by a limit in which u goes to 0. This is non-trivial, but we also argued that in the paper in which we showed this, and which is this. And it turns out that what happens is that you can trade that integral, which is quite non-trivial, by a limit in which u goes to 0. So there's a sense in which this seems more natural because you're just taking correlators in a CFT and restricting them to a time slice, and then you generate this structure. And by the way, just a comment that, I mean, correlators in CFT, they usually don't have these delta function singularities. They are like this power law behavior, while the ones in celestial CFT, they always have these delta functions in the sphere, and we can reproduce the delta functions in the sphere from this prescription, the exact delta functions that are predicted in flat space. So in conclusion, I mean, asymptotic symmetries in asymptotically flat spacetimes. Yes. No, I agree. I agree that it is guaranteed, but let me just comment two things. Well, at this point here, the only dynamical information is in the OP coefficient. I know that everything else is fixed by kinematics. And another thing is that everything was guaranteed by kinematics, but was also an important check that everything was fine, because this is a very non-trivial calculation. Although it's something that should happen and it's simple, the way it happens is non-trivial. The way this structure here emerges from this using this is non-trivial. And it's just it can be understood just as a warm-up to 4-point functions, which is where the actual dynamical information will be. So, as I was saying, asymptotic symmetries in flat space, they are related. They have important implications in scattering. As I said, I just gave a few results, but for example, there is implications for infrared divergences, for example, which are very important as well, among many others. I also didn't mention the memory effect, which is basically a way in which these things can be potentially measured. And in particular, I mean, the central thing I've argued here is that in gravity, they suggest that scattering amplitudes in a gravitational theory should have some kind of two-dimensional conformal symmetry. And that the correlators, these two-dimensional celestial correlators, these amplitudes, they could potentially emerge from a two-dimensional theory. But alternatively, one can try to extract these celestial amplitudes from a CFT in higher dimensions by a dimensional reduction, as I have explained. So I'm just mentioning here a couple of open problems because I think it's important to mention that we don't have at this point an intrinsic definition of a celestial CFT. I defined a celestial CFT to be a two-dimensional theory whose endpoint functions compute celestial amplitudes. That definition depends on the bulk, on the scattering in the bulk. We don't have at this point a complete intrinsic definition of a celestial CFT. Conformal field theories, they are defined independently of ADS. One can just define a CFT and study a CFT independently of ADS. We don't have that at this point for this celestial CFT, so this is one very important problem to be addressed. Another thing is that we should, related to that, we should try to understand whether celestial CFT, if it exists, is a two-dimensional theory, two-dimensional conformal field theory, or a different kind of two-dimensional theory which is not a conformal field theory. It just has conformal symmetry, but is different. It could be. Related to that is understanding the correct structure of the celestial OP. What's the mathematical structure underlying the celestial OP? Because as I said, I mean, it resembles an OPE, but it has some problems that have not been elucidated yet. For example, the question that what happens when we include both Z and Z bar terms? The celestial OP has been manipulated in 2,2 signature up to this point, where Z and Z bar become independent real variables, and then one keeps one of them fixed and expands in the other. But including all terms, there are some puzzles that appear, and there are things to be elucidated there. Another thing is that we need to understand these soft symmetries beyond the tree level, especially when we go beyond the subleading one. So subleading forward, we need to understand the corrections to these symmetries, loop corrections, effective field operators, and so on, because we need to understand to what extent they constrain a theory of gravity, and for that we need to understand how they are corrected. And finally, we need to understand, I mean, what can we learn from these celestial CFTs and from flat space scattering more generally, from conformal field theories using this dimensional reduction that I presented. Up to this point, as I said, this framework here is rather new. It's something that we have been developing it for the past 2 years. But there are still many things to be done, like 4-point functions and many other situations in which actual dynamical information will be available. And just another point that I want to make, the question about celestial CFT or not, I don't think is really a question of existence, because if you have a collection of n-point functions, it defines a theory, in a sense. But it's rather of what properties it satisfies, and whether it's useful in the sense that we can actually construct intrinsically such a theory and use it to define the scattering. And that is the thing that is not clear at this point, and that we need to understand better, and that's an important open problem. So yeah, that's what I had to say. Thank you.
Questions? Yeah. Obrigado, Nathan.
Thanks for the lecture. So I don't know much about gravitons, but I do know about the soft pion theorem.
Mm-hmm.
But the standard understanding of this is that it's a consequence of chirosymmetry breaking. So I'm just wondering if there's a relation between these asymptotic symmetries and spontaneous symmetry breaking.
Yeah, there is. I skipped, I didn't talk about this, but what happens in gravity, for example, is that these asymptotic symmetries, for example, supertranslation symmetry, just one second. Yeah, we have this field CAB here. And what happens is that after you define certain boundary conditions at the two boundaries of Scry, at the two boundaries of Scry, this CAB here becomes like a differential operator in AB acting on a function C. One function at Scry plus and another Scry minus. What happens is that you can instead of work with the two functions, pick just the one at scribe plus and the difference. The one at, scribe plus minus and the difference. The one at scribe plus minus, it, under a super translation, it gets shifted by F. So the super translation F maps C to C plus F. So it behaves as a Goldstone boson that is associated to symmetry breaking. So these, the super translation symmetry is spontaneously broken, and just not the four global translations not. But apart from the four global translations, they are spontaneously broken. And the same happens in QED for the large gauge transformations and Yang-Mills, for example.
It's very interesting. Thank you.
Yeah.
Other questions?
Not Cairo. I mean, he was asking if there was a relation between these symmetries, the soft graviton theorem, and some symmetry breaking. It has nothing to do with chiral symmetry breaking. It has to do with the large gauge transformation breaking.
So I have a question, very, very simple question.
Yeah.
Suppose that you have unlimited amount of resources, unlimited. How would you test this proposal?
Right. Well, there are two things, right? I mean, one of them is that these symmetries here, they're related to a measurable effect called the memory effect. So these super translation charges here, they can be measured through this memory effect, which is this effect that we have basically two detectors near scribe plus, and a gravitational wave passes, and it generates one net displacement between them. And this displacement encodes those charges. That's the idea behind that. What happens is that this is being, people are trying to measure that. So the memory effect associated to the super translation symmetry is something that is being tried to be measured. And associated to the super rotation 1 is there is also a memory effect called the spin memory effect that also people are trying to measure. But it seems that the leading one, the super translation one, which is the standard memory effect, displacement memory effect, this one, it seems that there is more prospect of being measured first than the other. The remaining things that I talked about, I agree that, I mean, at this point, I mean, one still needs to understand, for example, going further down, at this point, I mean, most of what I talked about is the reorganization of data for scattering. Now, this stable infinity symmetry should have some dynamical implication that I'd say that is not completely understood at this point. And then it should have some measurable effect, but it's not clear at this point.
Let me see if I understand. So as far as I know, this memory effect is when a gravitational wave passes through say, two mirrors.
Yes.
At the end, they don't return to the same distance.
Exactly,
Is that
yes.
correct?
Yes.
Do you have any, before going to all this, do you have any intuition why this should be so? Why, after passing a gravitational wave, the mirrors would not return to the same point? Because I don't. This is why I'm asking you.
Yeah, because, I mean, the point is that the gravitational, what happens is that when this gravitational wave passes, it induces a super translation in the geometry.
But this is not an intuition. This is a mathematical statement.
Well, another thing that I can say, I mean, I'm not sure how much it helps with intuition, but one thing I can say is that this, okay, it's not very good for intuition because it's a quantum statement, but if one thinks about what's happening when one does this super translation, one is basically shifting the gravitational vacuum by adding a soft graviton. So one is changing the vacuum. You can take the vacuum and add a soft graviton, and it remains a vacuum. The super translations add soft gravitons to the vacuum, so one shifts this vacuum. That's what's happening. I'm not sure if that's good for intuition, but
okay, better. Any other questions?
So I can rephrase what, I mean, I'm also a little bit confused. But so classical gravity is just ordinary Einstein's equations, right?
yes.
So can't I say what these symmetries are just by looking at Einstein's equations? Why do I have to talk
Yeah.
about infinity? So the first one that you found, that Weinberg found, that's just gauge symmetry, right?
Yes.
It's just, so there's nothing magical
Yes.
about that.
Yeah.
But why are the others, why do I have to talk about infinity? Why
No,
is
one can try. One can definitely try to understand what they do in a full space-time, not just at infinity. But it just happens that it's a bit harder to understand. But for
I just
example,
want to define it. So I still am confused, like George, about what the definition of a super translation is.
Does it have anything to do with the fact that these gravitons are so soft that they go to infinity and have some effect on what's going on around?
yes, yeah, because I mean the fact that they are soft means that the wavelength is very long, right? So they probe infinity, right? The wavelength is very
okay.
long, and but
I'm
another
very confused, but anyway.
But people have tried to understand what these transformations do to the bulk of the space-time. And then, for example, for super rotations, there are basically
Just for
different
QED, I'd
proposals.
be happy with QED. I don't even need to do
QED
gravity.
is the one that has let's say, the most clear example, which is in the Linear-Wickert solution, in which you can define these charges, and if you want, you can compute them in the, not at infinity,
But
you
is there
can
a
compute.
symmetry of electromagnetism which has this, that I can see? You know, I do this transformation and the Lagrangian stays invariant.
Yes,
Oh, okay, so what is that symmetry? That's what I'm
it's
asking.
the gauge symmetry.
No, but I know
But the
what
gauge symmetry, if it does not vanish at infinity, it has a consequence.
So any theory of electromagnetism with the gauge, any theory of F built out of Fs has the same symmetries.
Yes.
I see, okay. Okay.
We have time for a last question.
Well, thank you for the talk. I would like to ask you about the function that we have defined here, and
okay.
I understand that the super translation that we are defining, it's like you have some general transformations that are generated by that function, right?
Mm-hmm.
So my question is, since we have some infinite, I suppose, infinite dimensional generators of these kinds of transformations, shouldn't we get some infinite numbers of conserved quantities or, I mean, charges?
Yes.
But in this case, it seems like they are only two at the flat space that you have shown. I am...
No, but for example, in classical gravity, in the classical theory, you're going to equate Q plus and Q minus.
Yes, but
for
they are...
any F.
Okay.
So,
Then?
and then, okay, that provided you have the antipodal matching between this guy at square plus minus, square minus plus.
Okay.
If you have that, then, okay, for any function, you have a charge. And you can alternatively, well, write this in spherical harmonics, and then you think that for each L and M, you have a charge.
Okay. And one more question. That NA that we have defined there, it's in terms of some C that we have defined some...
This N, no,
Yes.
sorry. This N is, this N here
yes,
is the
one.
bond-in-use tensor. The bond-in-use tensor is like the F in electrodynamics.
Okay.
But the N appearing there is not that. It's the angular momentum.
Yes, and...
It appears
okay.
at further subleading orders. You need to go a bit more. I mean, I didn't write, but...
Okay, okay. This term that is, it's related with the C that we have there, right? You have defined it as some gravitational shear, I guess?
Yes, C is the gravitational shear.
Yeah, what's the meaning of that? What physical meaning does it have?
Well, there are two things, right? One is that it's the leading correction to the sphere metric. So at leading order, the metric of the sphere is just the round metric. Then at subleading order, it is not anymore the round metric. You get a correction. And its derivative, the News tensor, encodes gravitational radiation, encodes gravitational waves.
Okay. Okay.
So that's basically it. But it encodes more. But C encodes more because C also encodes the soft modes. So it encodes the soft graviton mode, which is that current I wrote, this P here. And it encodes also the other field, which is the Goldstone, which is the field at square plus minus, which is the one that shifts under super translations.
Okay.
So there are two things in C. The gravitational radiation plus this extra stuff.
Okay, well, thank you.
No problem.
So let's thank again the lecturer, Leonardo.
Thanks.